What I'm saying. Oh, July to August. I'm going to right?
Yeah, on the round.
That's why you're not having some other people on how much they. So. Before, I want both of them to test. That way, of course, if you right? We're looking for maybe our whole team.
You can get insensitive buttons last year where you can touch sensitive.
You like the feedback?
Yeah, like this here, there's tons of them. Here. Right, I order double master every day. Actually.
Yeah, thanks. Let's not go through the same thing as yesterday. I'm testing you too often.
What I see, like, I see the.
Okay, so breakdown for the test one more time, just for clarity. There is section on finding the results and adding the vectors graphically, head to tail, like visually adding them. So test. Okay. Finding components. X and Y components. All right, finding X and Y components. Adding vectors mathematically. Mathematically. For cliff problem, 5. At an angle problem. So throwing at an angle. Okay. And I will have some questions on this later. I got to get it at break though. Do you have them? With solutions, but I get that later. Okay, so I'm going to backtrack just a little. 103, yeah. Sure. Did we go over 103? I don't think we did. They're pretty easy answers, but I just want to highlight a couple things. Jake, is that enough? You got it? Cliff problem. Okay, let's just go over it quickly. Yeah, okay, number one. Then I'll start with page 108, but 103 first. Okay. So what is the weight of this object on the Earth's surface? So we know on the Earth's surface, I'm just going to use the absolute value. That's gravity. The mass is 25 kilograms. Okay. That doesn't change. Doesn't matter where you are. On the surface, above the surface, another planet. Mass is a measurement of the quantity of matter. How much stuff there is. This is the symbol for weight. Also stands for force due to gravity. And that can change. Why can that change? Because it depends on this. That value can change depending upon where you are. On the surface, we always use 9.81. So that works out to be 245. Again, it's a force, so it's measured in newtons. 2.5 times 10 to the 2. About 250 newtons. 2, what's the mass? And again, yes, getting back to this, it's down. I tend to focus more on magnitude when I talk about weight, but yes, it's always pointed down. Weight's always down. What is the mass of an object if its weight is 80 near the surface of the Earth? Okay, the confusing part here is that G is just a subscript. That G is 9.8 on the surface, 9.81. So this works out to be 8.2. Unit for mass is kilograms. Three. Just read that over. This can change depending upon, yeah. 103. I think we did it in class yesterday. Yeah. I just didn't highlight certain things, so I wanted to make sure I went over that. Okay, this value can change, what I just pointed at. It's 9.81 on the Earth's surface. On the moon, it's going to be far less. Let's see what it is. About 1.9, but let's calculate it. Actually, I'm wrong, 1.6. And yes, I mean, I just calculate the absolute value, but it's always down, right, or negative. If you see the word magnitude, that means just give the absolute value. Don't worry about direction. Or some magnitude of the weight. Weight is the same thing as force due to gravity. So approximately, yeah, I was going to say 710. So 706 newtons. It is down. It just asked you for the magnitude. That's the magnitude. Okay, this is calculated quite a lot. So what is the mass? Just divide the weight by 9.81. So it's about 13 kilograms. Okay. Now we can turn to, going back to here, page 108, 1 to 3. Okay, let's go over number 1. Just read through that. I'll go over it. Normal force of an object of mass m. Remember, when you're drawing a free body diagram, I'm going to draw that in a second. I'm just putting arrows on the diagram itself, then I'll separate it with the free body diagram. FG is always pointed down. Now here's a free body diagram. It's basically the same thing, except you represent the object with the mass. There's your FG. The normal force will react in the opposite direction, and it's equal. Okay, it's perpendicular. If the surface was here, that's the free body diagram. You don't add anything more to it, just the forces. And label the forces. So if we know what FG is, since Fn is equal, we know what Fn is. Okay, so 137 bigger than 100, put it in scientific notation, round to 2. 2 or 3 is fine. So you could write it as 1.37. Magnitude, that's all I wanted. I know it's upwards. Normal force is always pointing away from the surface. Pointing this way. And perpendicular to the surface. Normal means perpendicular to the surface. Okay, 2. Read that. Okay. Friction. So you should have read in the textbook just as a review. This formula will change depending on what type of surface and what's leaning on the block. But if you're just pulling a block along, if you're not pushing down on it and it's on a level surface, that's key. It's not on an incline, it's not on a slant or a hill. It's a level surface. That's your force of friction. Okay? In general, where does that come from? This is the general equation. Gentlemen. General equation. That works under all conditions, level surface or incline or hill or otherwise. It just so happens on a level surface, we mentioned it above, Fn is Fg on a level surface. That's why I was able to get this. Okay. This is the most important because it's general. It can be used in all, that's supposed to be a star. In all situations. Okay. So in this particular case, again, mu mg, where this is what we call the coefficient of friction it's usually less than 1. It's usually a decimal. The measurement of how rough the surfaces are. M is mass. G is 9.81 on the Earth. Okay. So let's plug it all in. Works out to be, I can't even read my own. Yeah, it looks like it's 10 newtons. Rounds off to 10 newtons. Okay, and friction always is acting opposite to the way the object moves. So I'm assuming this object's moving to the right. Friction will act to the left. You can write it as negative, or you can just indicate to the left. On a surface to the left, or you could say, if you want, to the west, westerly. Three. Read that. Now, here's an important point. I'm drawing the free body diagram just to show you visually. I haven't drawn the friction in yet, but the key phrase is constant speed. You want to pay attention in a problem to the phrases such as constant speed. It is not accelerating. That implies not accelerating. Okay? Acceleration is 0. F net is 0. When there's no net force, that's another way of saying force is balance. Which forces? Well, it's moving this way. Moving to the right, it could be moving to the left. Usually we just assume if they don't say anything, it's moving to the right. Which force is balance? The force that's pulling on it balances, the force of friction. I tried to draw it equal length. They should balance. If they didn't balance, let's say FA was bigger, then A would no longer be 0, be some positive value. So friction is equal to UMG. And let me check his forces. Sure. Yeah, okay. This is the weight. Remember, this is the weight in newtons. Mg is the weight. Keep that in mind. Friction in this case is just equal to Fa. And Fa is 3. Remember, this is the weight. So if we read the problem, they don't give you the mass, they give you the weight. They say it's a 20 Newton object. 20 Newton object. Look at the unit. Implies weight. I just plug in 20 here. So 3, that's a 3.0 over 20. 0.15. No unit. Yeah.
So with like a object at rest, if like the net force is 0, it still won't move. But then once like net force becomes like positive, it will start moving.
Yeah, you're thinking. Yeah, I know what you're thinking. If an object's just sitting there and the net force is 0, if the forces are balanced, it won't move. But if it's already moving,
and then once
what usually happens is this, like with the car, the FA is bigger than the friction, than the resistance, so it starts to accelerate. And if it's a car, let's say you reach some speed of 50K, 50 kilometers per hour, and you want to maintain 50K, you decrease your power, you level off on the pedal, right? And the FA would decrease to balance the resistance. In that case, the forces are balanced, you just keep moving at 50K. But yeah, I know what you're thinking. You do have to accelerate to get up to a speed, but once you're at that speed, you can level off on the force and balance them and continue to move at that speed.
Is it because once you get moving, the friction is reduced?
Once you're moving it's reduced a little. It's reduced a little, but in order to reach any speed, you've got to have an applied force greater than that friction. Yeah. Um, okay. Yeah. So the next page, what the heck did I do? Okay. Next page is this one here, 108. Just did 108, 114. Actually, before we go on to 114, I wanted to add, we'll come back to 114 in a second here. I wanted to go over inclines with you. And then I wanted you to try 4 and 5 out. But you may already know how to do it, but let's go over incline. So add this to your notes. Okay, so what do I mean by an incline? It's a hill. That's what an incline is. If I were to draw it, look like this. Okay, I'll use an angle here. It could be any angle. I'll use 30. I'm not worried about calculations, but I'll use 30 for our convenience. Okay, what we're interested in is objects that are placed on this incline and the forces acting on it. This object has a mass m. It's a mass m. FG is always acting down. That never changes. Always pointed straight down. Even though the surface is slanted, FG is pointed down. And the normal force is always perpendicular to the surface. So normal force is this way. Perpendicular to the surface below it. And if I were to, I'm going to erase this in a second, but if I were to draw a parallel line parallel to the surface, it would look like that. Okay. So this is the normal force. Okay. Obviously, the normal force is reacting against something. It's reacting against what? It's reacting against a component of the FG. There's a component of the FG that's perpendicular to the surface. We'll call this FG perpendicular. So Fn is reacting against that. FG still has a part of it that's pulling this block against the surface of the incline. So we'll come back to that. We can add another component here for convenience. We like working with perpendicular components that form a right angle triangle. This green arrow, what I just drew, this latest one, I'll call it FG. It's also part of FG. It's a component of FG that's parallel to the surface. It's parallel to this. I'll call it FG parallel. Okay, FG parallel is what causes the block. If I were to let the block go, FG parallel causes the block to accelerate down the hill, down the incline. That's what's doing the acceleration. So if we know what FG is. FG obviously is mg. Obviously mg. We don't know what FG parallel is or FG perpendicular is related to this. We don't know how it relates to that. We can figure it out though. This angle here is the same as this angle here. I can prove that geometrically. Okay, I'm just going to tell you that, but you can redraw this. This is 30 degrees. That's the trick. And then this is, let me just relabel it. This hypotenuse is FG. Okay, so I want, first of all, to find my FG perpendicular, because then I have my FN. FG perpendicular is the adjacent side. If you look at this triangle here, FG is the adjacent side. This side here. This is the hypotenuse. This is the adjacent side that forms this angle. So that's a hint as far as what trig function I should use. Adjacent implies use cosine. So what have I got? I have cosine of 30 degrees is equal to the adjacent over hypotenuse, which in this case is FG perpendicular over FG. Let me just rewrite it here. Now I'm going to cross multiply. I'll cross multiply FG with cos. I'll put it in front. It doesn't matter. It's just, they're just numbers. 2 times 1 is the same thing as 1 times 2. That's my FG perpendicular. Yeah.
What is the line between what goes to FG?
Oh, this here? This here means perpendicular. Sorry about that. This means parallel. 2 lines parallel to each other. This, what I just said, upside down T is perpendicular, 90 degrees. Okay. FG parallel is the opposite side. Opposite to the angle 30. That implies, that's a hint. That means try using the sine. Let's do that. Sine of 30 is opposite over hypotenuse. Opposite is FG parallel. Two lines next to each other means parallel. Side by side parallel. Over FG. Do the same thing. Cross multiply the FG with the sine. So you get FG times the sine is equal to FG parallel. Those are there's one more formula, but those are the two main ones. Why is FG parallel important? Because that's what's tugging it down the hill. Pulls it down the hill. Not FG completely, but just part of it. Just part of it, the parallel component. Pulls it down the hill. Like I said here. FG, I just said it here. FG parallel causes the block to accelerate down the incline. And one more point here. FG perpendicular is important because it's equal to the normal force. So let me write it out here. Rewrite this. We have FG parallel. I'm just rewriting it. We have F G perpendicular, which is the same thing as Fn. Which is FG cos. This should be perpendicular. Now, one last point. Friction is always mu Fn. Always. What is Fn in the case of the incline? It's that Fg cos. So friction in this case is these are, I would say, if you were to you want to memorize, that's fine. I will not, I got to look at your formula sheet. I don't think it's on there. I'm not going to give that to you. So you need to either memorize it or know how to derive it. I would know these two. Those are the most commonly used. You got a question? You want to take a picture?
Yeah.
Which one? The whole thing?
Yes.
Sure.
Okay, so when it says that basically this, if you make those automatically are the same, how it works, but
Okay, take a minute just to go rehash that, go over it, review it quickly. See if you can,
can you zoom in a minute?
like zoom in like that.
Yes.
Is that part there?
Yeah, from the start. Mr. Kelly, so we should always use the parallel force of gravity to calculate this.
One in calculating the acceleration.
Acceleration.
And then the perpendicular part when calculating the friction.
Oh, will there be any use for the original force of gravity beyond the derivation of like these two?
I mean, not on the incline problem.
Can you go down?
Yep. There?
Yes. We'll be given homework for this week practice, right?
Yeah, I've got some worksheets on it. I
Yes.
can give it, you're
Thank you.
welcome. I can give it to you later though. I've got to highlight key features on that. But this was just a little intro. There's some questions coming up next, but just look it over again. Some of you are sleepy. It's okay. I understand. I understand. Okay.
That's a big change.
Shane.
Yeah, big change.
On page 108, four and five, just give those a quick try. Those are making use of, I think it's a second and third equation here. I turned my phone off.
No, not like that. It's like this. It's slightly different. Yeah, that's one point. How did you do it? Because like, it's perpendicular.
What is on here? It should start.
We'll go over 108 in a second here, 4 and 5, but then we'll move on to 114. Can I try? I gave them the wrong.
Yeah, opposite over hypotenuse. Hypotenuse. Wait, so this is the. Right? So this is like a perpendicular force. And the perpendicular force is the same as the normal force. So force normal is 7.
Okay, let's go over 4. So it says an object is at rest. What's the magnitude of the normal force? Normal force is just equal to this, Fg cos of 30. Yep, got it. Cos of whatever the angle is, pardon me. In this case, the angle is 25. Okay, Fg is mg. They give you the mass, you have to use mg. That works out to be 1.4 times 10 to the 2 newtons. And it's just asking you for the magnitude. So it's about 140 newtons. Five. What is the magnitude of the friction? Friction is this here. $25, what's the unit? Is it 25? It's 35 this time. 35. Coefficient is 0.3. We're told it's a 15 Newton object. That whenever they spell out an object is so many newtons, that means it's an FG. That's the FG. Okay, that works out to be 3.7 newtons. And it's just asking for magnitude. Yes, friction is, in this case, if the question, it's an important point, sometimes we miss, so don't get confused. If they say magnitude, just give me a number. If they ask you for the friction, that means that implies direction as well. So in this case, it's being pulled up, Friction is always, and it's moving up. Friction is in the opposite direction. Down the incline. So pay attention to what the question's asking. It says magnitude, just do what I did, just give a value, 3.7. If it just says friction or force, calculate the force, give direction as well. Now I can do page 114. Yeah.
What is calculated for like, let's just say number 4?
Yeah.
Isn't it something like cosine 25 equals like a base over hypotenuse? And like the adjacent will be the force of gravity, which is like going directly downwards. And wouldn't that mean like it would be like force of gravity divided by cosine 25 equals the normal force?
This, if you look at, okay, I don't know if this helps, but you're gonna have to just trust me. I mean, I could show you geometrically that this angle here, which is what I use, which works out mathematically with what I gave you, that angle there is always the same as the angle of the incline.
Oh, because if you draw it like that, okay. Because
That's-
like the force of gravity
that's-
becomes the hypotenuse.
The force of gravity, it forms a hypotenuse in the way I drew it, yeah. Okay, you just have to accept the fact. I mean, again, let's not spend extra time figuring out geometrically, but that angle is equal to the angle of the incline. What?
Because it has to be parallel to the slope.
You want to draw? Is that what you said? You had to do on page 114. That's what we're going over next. Okay? That was part of the homework from yesterday. 114, 1 to 6. Okay, so I'll read over number 1 to yourself. I'll go over that. Okay, I'm going to draw a free body diagram. You throw an object up. We're interested in when it leaves your hand, not when it's in your hand. It leaves your hand. When it's actually, we're interested in the moment it leaves your hand. The moment it leaves the hand, you're applying a force to it. Force of gravity is acting downwards on it. Force of gravity is always acting down. It is, notice how I drew the force of gravity. I drew it as smaller than the applied force that your hand is exerting. Okay, so this is the moment just before it's released. You're applying this force. Question is, what's the acceleration? So when you have an acceleration problem and there's forces involved, this equation should come to mind. That's always true. What can change is the left side. What makes up the left side depends on this diagram. That's why we draw it. So for this particular problem, F net is made up of an applied force, and then subtracting from it is Fg. It's acting in the opposite direction. And this is just absolute values. I'm just using, I always write the larger force first. I don't care whether it's up or down. I'm using this equation and calculating the absolute value. So the rule is write down the larger force first and then subtract from it the smaller one. Fg is always mg. I'm dividing both sides by m. Right, divided both sides by m. Put a line under both terms. The m's will cancel out on the right. You get this. Okay, The applied force is 145. The mass is 11. $110.35. It's what is that? 3.5, 3.4 actually. Okay, they just ask you for magnitude. If you look at it, it just says magnitude. That's what you'll calculate the magnitude. Now, if the question was, what's the acceleration? The question was simply, what's the acceleration as opposed to the magnitude? You need to include direction as well. That's another reason why you need the free body diagram. Free body diagram tells you, by looking at it, you can tell the FA is the dominant force. So this is upwards. This is up in the direction of the larger force. The larger force determines the direction of the acceleration. Okay, read over 2. I know you may not have done it, but when you're doing a net force problem, I would include a free body diagram. I'll be looking for that on a test, so include it, get used to it. Free body diagram includes only the forces acting on the object. Why is it doing that? Okay. So it's moving to the right. Assume it's moving to the right, accelerating to the right. It's these two forces that are involved. They're going to be involved in the equation. Not the normal force and FG balance each other. I'm not finished. Okay. So the question is, what's the acceleration? It's always equal to ma. Keep that in mind. This is always true. I don't know what this expression is. It depends on the free body diagram, on the forces accelerating it or acting against it. So what are those forces? It's FA accelerating it. That's the larger force, so that comes first. And anything acting against it is subtracted. And I want to solve for in this problem the acceleration. Okay, let's just look at this. This is the equation. I have my FA. I have my force of friction. And I have the mass. I can just plug in. So 4 over 12, so what's that? 1 over 3.33. So this works out to be 0.33 meters per second squared. Notice the question is, what is the acceleration? There's no mention of magnitude. So pay attention to the question. If it just mentions acceleration, then you need a direction as well. It's accelerating to the east. That's the direction of the applied force. So this is east. You can add that at the end. Now I can answer. Yes.
In this case, we only focus and apply for the
Include these two as well because that's a free body diagram. Yeah. Just realize only FA and the force of friction are included because they're in the direction that it's accelerating. The other two balance each other. So they're not part of the equation. Okay, number 3. Okay, let's go finish this. We can get through this. 3, have a read through it. I'll go through it in a second here. Okay, I just drew the free body diagram. It's the same as number 1. The difference is in this problem, you're solving for the applied force, not the acceleration. You're solving for this. That's what you want. So it's the same equation as number 1. Same as this, it's that. Except you're not rearranging for the acceleration, you're rearranging for this. FA. So rearrange for that. Add FG to both sides. And then doing that, you get where FG is mg. Use only, with the way I'm writing it out, use only absolute values. You can figure out the direction at the end. If you've written this properly, use absolute values for A and for G, and then you can, by the diagram, figure out the direction if you need it. Yeah. Stopped transmitting. Stupid Google. Okay. So 15 times 8.8 plus 15 times positive 9.81. Just use absolute values with this equation. It'll work out. So that is 132. Yeah, 147. Good. So this is 280. And the question is just the magnitude. That's all you need. Okay. 4. Read it over. This same problem as number 2, except they're asking you for the friction. I'm not going to redraw the, I'm going to save myself a little time. It's the same diagram as number 2, same equation up to here. I'll just write the equation. Same equation as number 2, same diagram. Okay, I want to solve for friction. Add it to both sides. Cancels out here. Subtract MA from both sides. That's my friction. Applied force, I'm just plugging in numbers now. 27, mass is 20. This makes sense. No, that's not acceleration. Made a mistake. Acceleration is 0.8. That makes sense. Well, this works out to be 11. And they just ask you for the magnitude. So that's enough. Okay, almost done here. 5. Read that. Okay, if I know what the F net is and the acceleration, I can find my mass. So if you read the problem, the key phrase there, again, pay attention to key phrases, is frictionless. No friction. So the free body diagram for this is simply just that. There's no friction in the diagram. So the only contributing force is FA. That is the net force. If there's only one force, then that equals the net force. So the net force is FA. So net force over the acceleration is the same thing as the applied force. So I have the applied force. I'm given that. I don't have the acceleration directly, so I have to calculate it. Gentlemen, gentlemen in the back, Jake, just talk about it later. I'll give you a minute in between this problem and the next. If you guys want to talk about it, it's fine. Acceleration, I need to find. So let's make a list of what we're given. We're given the initial speed is 0, accelerates from rest. Final speed is 4. The distance it accelerates is 5. And you want to find the acceleration. That's your list. So your acceleration is 1.6. Okay, to the right. Doesn't matter, we're not going to use direction here. What we need is just the FA and the A, which we have now. Works out to be 7.5. That's your mass. Take a minute just to, I'll go over the last one in a minute here, but take a minute if you need to discuss things, that's fine. Coming up to the break in one couple minutes. Okay. Number 6 is just number 1. Same equation, same free body diagram. So number 6 is, I'm just going to rewrite the equation. That's it. Except it's asking you for the applied force, so just rearrange for that. Everything's that you use to plug in is absolute value, positive values. Yeah, that makes sense. 65 newtons up. It just asks you for the magnitude. It's 65. Okay. Take a break. Be back here by 10. Giving you a couple more minutes because I got to photocopy stuff.
Yes. That's what we want, because, like,
Did I lock this up? I'm going to lock it up.
we'll go ahead and
Susan, you got it? Yeah. Wrote it all down. Anyone not? Okay. 5, 4, 3, 2, 1. I'll be back. I feel like Arnold Schwarzenegger, but yes.